Hello, everyone. We're Team F3 Optimus Dine, and we're very honored to stand here before you to present our journeys over the past few months of tackling the 2022 Robot Challenge. We'll begin with introductions. I'm Nicholas Chong, co-lead programmer.
I'm Brad Shaw, also the co-lead programmer.
I'm Pete Spoffworth, constructor and project manager.
And then I'm Jack Sweet, and I was the lead mechanical constructor.
Today, we'll be discussing the preliminary ideas and concepts that we had coming into the project. Then we're going to move on and talk about how we planned for the competitions in the following months, and as well as their results. And we'll end the presentation talking about our overall journey with the project and any questions that the audience may have. So we'll begin with ideas and concepts. And the main concerns that we had coming into the project was what was the best route that we could take, and if we could do everything with one arm, and if we could even stay within our budget. And most importantly, we just wanted to know what was there to simplify for our robot so we wouldn't be building Optimus Prime.
As Nick mentioned, in order to start creating design concepts, we first had to determine a course strategy, as well as analyze each of the tasks on the course in order to design a robot that could meet the specifications of those tasks. After doing so, we came up with three initial designs. As you can see in the top right, we have a three-wheeler design with a two-wheel drivetrain and one omni-wheel in the front to allow full mobility. This design features multiple robot arms to complete each of the tasks on the course. However, one drawback was the wheel jutting out in front of the robot, preventing it from having any bump switches on the front side of the chassis. Similarly, in the bottom right of your screen, a similar design was the two-wheel and two skids design. It also featured multiple robot arms. However, it used skids in the front instead of provided greater stability and did not block the front of the robot. However, it also caused increased drag. The third design that we eventually decided on was the triangular and omni-wheel design. This design featured only one robot arm, which would complete all the tasks on the course. However, as you can see here, after building a prototype, we soon realized that this design would be unrealistic. The one arm feature would not work with the course, as all of the tasks are at many different heights and it would not be compatible with many of them. Additionally, with the way the wheels jut out on the sides of the robot, using micro switches would also be unrealistic, which takes away a great navigational tool, as well as having to buy a third motor puts an increased strain on the budget. I'll pass it over to Jack, our constructor, to talk about the initial design that we did end up going with.
Thank you, Pete. So after scratching the omni-wheel design, the team went back to the drawing board and ended up merging the other two options. We liked the idea of the square base. It allowed room for the micro switches, fixing the problem Pete previously stated. Instead of using the front omni-wheel or the skids, we decided to go with a caster ball. This allowed for sharper turns and also got rid of the problem of increased drag from the skids, and it didn't take up any space on the robot's base. We opted to go for a two-wheel drivetrain powered by Iguan motors, and this was our final robot design. It features an MDF chassis, which was super easy to work with and durable. In the back, you have Iguan motors with 3.5-inch Dubro wheels. The Iguan's shaft and coating, along with the rubber bands, allowed for super accurate navigation and straight lines. Our robot features 3 servo mechanisms, the first being the burger mechanism on the front right of the robot. It was super simple. It just has 2 prongs that stick into the revolving wheel and flip the burger, creating the perfectly cooked patty. On the front left of the robot, you have the tray and ice cream lever. This mechanism functions by just lowering and raising a lever that dropped off the tray in a trick shot sort of fashion, and also was able to press the ice cream levers, creating the perfect 7-second twist for every customer. On the back left of the robot, you have the ticket mechanism, which was super simple. It just lifts a lever, drives forward, and then lowers the lever, leaving the ticket in the final position almost every time. The coolest feature about our robot was that the ice cream lever and the burger mechanism could be used to press the jukebox button. This reduced a lot of risk from repositioning the robot because it wasn't necessary. This guaranteed that the customers had their desired music in the Carmen's Diner. I'm now going to pass it over to Nick, who's going to discuss the competition plan.
Thank you, Jack. After finalizing the design as Pete and Jack stated and having a proper general idea of what the course was going to look like, we needed to create a more specified path. And that began with our course strategy. So as you can see here, we go to the sink and then to the ticket, to the burger, to the ice cream, to the jukebox, and then back to the start. We did this because we wanted a very simple path with limited movement. After taking in more measurements to make sure that the robot would go consistently to each task, we came up with 4 main concerns. The first concern was the movement before going up the ramp. Since we wanted to deposit the tray in a trick shot-like fashion, as Jack stated, we didn't want to run into the sink when going up the ramp, and that was a main concern. So we had to figure out what the distance was before moving up the ramp. The second big concern was moving to the ticket structure. We didn't want to run into the ticket structure either, so we wanted to make sure it was moving the correct amount so there would be a clean insertion of the ticket lever into the ticket structure. Our third main concern was moving to the burger revolver. This was a huge concern because it was the longest path between 2 different tasks, and we wanted to make sure that it was consistent every time so that the arm would go into the revolver correctly. And our final main problem was with the jukebox. We wanted to make sure that it would sit in the correct orientation every time, so it would read the correct CDS value to consistently push the correct jukebox button. Our next step was to go into and organize our code. As a main programmer of the project, we wanted to make sure that our code was very organized and easy to follow. And if anything needed to be changed, it would be easily changed with the press of a button. And that can be seen in our measurements here. And with having all of these constants at the beginning, all the measurements that we needed to change could be tweaked easily by changing a number here and there. And our next step was to make correct functions. These functions were precise, but also modular so that any combination of them could be used to perform a simple task. And here's a representation of our functions. More information can be seen in our website, but this just gives you an idea of the high levels of logic that we needed for our functions. And now I'll pass it on to Raj for our competition results after our long hours of planning.
Thank you, Nick. As everyone knows, there were 2 competitions to test the robot to its limit. Starting with the individual competition, where we combined our phenomenal performance test results. In the individual competition, our team's robot did quite well with moving the ticket, putting tray into the sink, and getting up the ramp. Our robot was consistently doing all these tasks in 1 minute and 40 seconds. While the competition was going on, we noticed some changes our team can make to allow the robot to be more consistent in doing the task for the final competition. As Nick mentioned, the robot was running into the sink while turning, so we decided to cut the corners to allow the robot to turn more consistently. Next, we added more functionality with RPS and calibrated more frequently, which allowed different tasks to be more efficient. Lastly, we added more heading checks so the robot can move in a straight enough line and get tasks more consistently. After we made these changes, our team felt more confident with the final competition. These changes allowed us to get a 90 out of 100, receiving all the primary points and getting one of the fastest and most improved time of 1 minute and 13 seconds. As you can see on the picture on the right, Nick is rolling on the floor of the competition as he knows our robot is going to be mass produced by Carmen Dining. Some final changes we can make before a robot is obviously mass produced by the Dining would be firstly adding a proportional integral derivative function to our software. The idea is a way for the robot to consistently move motor speeds faster or slower depending on where the robot is on the course. Lastly, we would make our CDS subtle funnel larger on the bottom of the robot to allow better range and more consistent light reading. Next, we will talk about the budget of a robot, giving it back to Jack.
So starting with a budget of $160, the team spent a total of $130, the majority being spent on the drivetrain aspect of the robot. However, we were very impressed with the $30 that we had remaining in our budget, as the Carmen Diner could produce our robots at a very cheap rate. I'm now going to pass it over to Pete, who's going to summarize the robot journey.
After many, many hours of production and testing, we came up with a robot solution that had a high level of consistency and speed. This robot came through merging multiple of our best ideas that we brainstormed all together to eventually create the perfect robot. Through the individual competition, we proved that our robot can succeed in the Carmen Diner environment and maximize Carmen Dining's profit with the additional bonus of being very cheap to produce.
And on that note, I'd like to thank you guys for listening. If there are any questions, ask away.